Hi everyone, my name is Abdulwali Abukar, and we're going to be solving the qualitative question that is posted on my webpage, and it's the one up above this video, and if you scroll up you'll see it. And we're going to be solving this question using the problem guideline that's presented right here, and we're just going to go through each steps. And we have A through I. So we have steps from A through I. So A through E is that, and F through I is that. So we're just going to be solving it step by step, and I'll be walking you through it. So okay. So our question. Let me just read it to you real quick. It says 2-point charges Q1 equals negative 1.1 times 10 to the negative 6 charge, and Q2 equals 1.1 times 10 to the negative 6 charge are placed on the x-axis at x of x1 equal x of 1 equal 4.2 meters and x of 2 equals negative 4.2 meters respectively. And it says see figure below. So there's a figure below, and it's a diagram of how that's portrayed. And then the questions that are asked are, what are the electric potentials at the points points P and R? And P is given, the coordinates is given, which is 0, 4.2 meters, and R is also the coordinates of R is given, 8.4 meters and 0. And the other question on part B says find the work done in moving a 1 times 10 to the negative 6 charge from P to R along a straight line joining 2 points. So in this question there's 2 parts to it, and part A we're going to be solving the electric potentials at point P and R, and the second part of this question is part B, and we're going to be solving the work from P to R. So tackling this problem on the problem guideline, over here we see that the first question, it says main concepts. So the main concepts we're going to definitely be dealing with is definitely going to be dealing with, so you can see this better, is first concept we're going to be dealing with is electric potential, which is voltage, and we're going to just write that right here. Electric potential, sorry for my handwriting. And another concept we're going to be dealing with is work and electric dipole is another concept. Electric dipole. The given information, well, there's a lot of given information, but it also says hidden information. So let's start with the given information first. So we're given Q1, and that equals negative 1.1 u sub C. Q2 is also given. Q2 is 1.1 u sub C. P is given, the coordinates of P, which is 0, 4.2 meters. R is given, which is the coordinates of 8.4 meters. Okay. What else is given? It says x of 1 at Q1, that equals to 4.2 meters. X of 2, it says that x of 2 equals negative 4.2 meters respective to Q2. We can also say, what else is given? We also given a charge that's moving from P to R, and that is we can call this Q3, and we could also label this it's moving from P to R. Q3 is moving from P to R, and it's also equal to 1.0 mu sub c. We could label P1 P because it has a y coordinate, so you could just say y1 equals 4.2, and we could label r as x sub 3 equals 8.4 meters. What else we can write? Well, hidden information would be the k constant. So k equal 8.99 times 10 to the 9 in units. So that's all the given information that we could receive from this problem. And yeah, so that's all the given information. So the next section is to write down your final quantity you're solving for in its units. Where A, we're solving for the electric potential at B and R. So in part A, you're going to be solving for electric potential at P, and that's going to be in terms of voltage. And also we're going to be solving with R, and that's also going to be in units of voltage. And in part B, we're going to be solving the work done of charge of Q3. Yeah, we labeled it earlier as Q3. P to R, and that's in units of joules, because that's work is given in joules. And if we predict the range, we can predict that looking at the, we can come back to predicting the range. Let's draw our diagram first. So the diagram is also given, so we can just kind of use it. So we can get it first as a visual representation. Next is going to be like Q1. Over here is Q2. Over here is R. Over here is P. And the P is gonna be at 0, 1, 1. Q is gonna be Q1 is x1, comma 0. Q2 is gonna be x2, comma 0. R is gonna be x3, comma 0. This is x-axis. This is y-axis. Yeah, and then we can also draw a Q3 over here, initial, and then Q3 again here, final. So we could find the work it did when it moved from point P to R. We can draw that, and that's going to be a quick diagram. But to predict the range, we could go back to predicting the range. So for A, we're predicting the for P, the voltage is going to add the electric potential at P at point P, and we can say that because Q1 is a negative charge. So let's just do a negative charge and positive charge here. Because it's negative charge and this is a positive charge, and is equally, x2 is negative 4.2 and x1 is a 4.2, and P is in the middle of both of them. Is located at in x of 0 at line 1, which is 4.2. I can predict that this charge and this charge, because of the fact that they're equal in magnitude and opposite in sign, and they're equally spaced apart, and the fact that I know of electric dipoles, and usually over here the voltage is 0. I can assume that it's going to be 0 at P, and then the electric point is going to be 0. And then for R, I can assume that over here we have the negative charge is closer than positive charge, so I can conclude it's going to be negative 1 to 9 at times 10 to the 3, because we're going to be using our charge, which is 10 times times 10 to the negative 6, and we're going to also be using our K constant, which is 10 to the 9, so it's going to be a magnitude of 10 to the 3. And then another thing we're going to also be using, so another guess we're going to be also guessing for is going to be our work, and the fact that our work is the difference between VR minus VP, because our Q3 is moving from P to R, is going to be R minus P, and the fact that R is going to be a negative value and P should be 0 for my prediction. It's going to be the same thing, the same negative value, because our R is negative and our charge is Q3 was positive, so it should be a negative value. And since this is going to be times 10 to the negative 6, I can assume that our magnitude is going to be times 10 to the negative 3, I believe, and that's going to be in joules, so it should be in that range. Okay, and we predicted that using the electrical dipole concept. So the equations we're going to be using are the following. Voltage equals KQ over R, and work as well, because we're starting for work, right? So that's going to be the change of voltage times Q, and K is the K constant, Q is the charge, and R is going to be the distance. So so let's prove, let's not prove, but let's solve in variable form, which is expected as in part G. And also, once you find the variable form and you manipulate it, you have to simplify the formula. So we're going to be doing that. So first thing we're going to be solving for is part A, and part A consists of the electrical potential point at VP, and we're going to denote V is the voltage and P is the point. So the voltage of P, that's what my VP is going to stand for, and that's going to be K times, so let's use our diagram here in a way. Let's kind of use it. Yeah. So we can kind of let me get that in shape. Alright, so we can use our diagram to help us. So we can say VP equals KQ. So we have two Q's that's affecting that point, right? So we have negative Q1, negative charge Q1, and a positive charge Q2. So we're gonna say KQ1, and that's negative charge. Remember that. So we're gonna note that it's negative, and we're gonna say plus KQ2, and that's the positive charge to help us remember. And the radius, the R is the distance, that's the radius. And the distance, if you look at this diagram, it's gonna, if you look at one portion of it, for example, KQ1, the distance is gonna be from here to here, and you can use the Pythagorean theorem, so you can say x1 squared plus y1 squared, square root that to get that R. So we're gonna do that right there. We're gonna say x1 squared plus y1 squared. And for for VP affected by Q2, do the same thing. This time it's going to be x2 squared plus y1 squared, and square root that. And that's basically our simplified variable form for VP. Yeah. But we can also denote this. We can also write this because the fact that x1 squared and x2 squared, it will give us like a positive value squared is going to be positive value, and negative value squared is going to be the same thing, and negative positive is going to be a positive value. And the fact that these have the same equal magnitude, so you can actually simplify this to k. And you could just pick either one. So you could just pick x of 1. Or actually we could pick x of 2 if you don't believe me. That's gonna be equal. So we could just pick up x of 2 squared plus y initial squared, so I can prove it to you guys. And that's gonna be multiplied by q1, which is our negative, what's it called? Negative charge plus q2, which was our positive charge. And that's gonna be a simplified version of that. And then now for part A, we also have V of R, electric potential at point R. And we're gonna also be using this equation again, which is our K times Q divided by R. So we're gonna start off writing down K Q1, and remember that was our negative charge. Divide that by our distance. So our distance is going to be x3 minus x1, because this time we're just on a line and not on a triangle. We're not trying to solve as a triangle. So it's going to be x3 minus x1, our distance, and then you're going to also, because R is not only affected by Q1, but it's also affected by Q2. So K Q2, which was our positive charge, remember, and that's going to be x3 minus x of 2, and yeah, that should give you your electric potential at R. And if we wanted to, and then at part B, we wanted to solve for, so this is equal. So at part B, we're trying to solve for the work, and the work is equal to change of volts. So it's going to be VR minus VP times our Q, and the Q we're using is this Q, which was given, and it's we labeled it earlier as Q3 in our given information, and that was also a positive charge, and that's going to give you your work. And now we're going to be using this, and we're going to be computing it. This was in variable form, so we're going to use all these variables and match it up with our givens to compute it using numbers. So we're going to be only work with our numbers using our simplified version. So okay, A for VP. VP equals to 8.99 times 10 to the 9, and the units on it is n squared c squared, right? and we're going to be dividing it by x of 2. X of 2 was the negative value, which was negative 4.2 meters, and that's squared, plus y1 we labeled it as 4.2 meters, and that was squared. And now all that is going to be multiplied by Q1, and Q1 was negative 1.1 piece of U plus 1.1 piece of C, our charge. So you see here, negative 1.1 times 10 to the negative 6 charge plus 1.1 times 10 to the negative 6 charge cancels out, so it's going to be 0. This is going to be product of 0. That's going to equal to 0. So 0 times anything is 0. So therefore we have 0 volts at Vp. So now we're going to solve for VR. So VR is going to equal, we're going to use our equation, and we can simplify this equation above. So we can take out the k. We're going to say q over x3, x1, q1 plus q2, x3 minus x1. That's positive. So we can simplify that, and we're going to use that simplified equation over here. I'm going to plug in our numbers like we did previously. So that's going to be 8.99 times, so let's make a squiggly line over here so we don't get confused, times 10 n squared c squared, over here, that's going to be multiplied by Q1, and Q1 was negative 1.1 times 10 to the negative 6 plus 1.1 times 10 to the negative 6 charge. This is divided by x3. x3 was 8.4 minus 4.2. This is 8.4 minus 4.2. So this is in meters, this is in meters, this is in meters, this is in meters, and that should give us a value, and we're going to compute that value on the calculator. So we have 8.99 times 10 to the 9, and we have negative 1.1 negative 1.1 times 10 to the negative 6 divided by, so 8.4 meters minus 4.2 meters is going to be 4.2. I have 4.2 plus 1.1 plus 1.1 times 10 to the negative 6 divided by 8.4 minus 4.2, that's going to be 12.6. It adds up together. Let me see if my parentheses are right. Yeah, it looks right. So we got the value of negative 1569.68254. In our equation, in our question, we have 3 sig figs from 8.99. So we could just use 3 sig figs, and it's going to be negative 1.57 times 10 to the 3 voltages times 10 to the negative 3. So now we can use this value for our work when we're trying to solve for work, and we can say negative 1.57 times 10 to the 3 voltages minus 0 voltages from VP times by our Q3, which is which our Q3 was 1.0, times that by 1.0 times 10 to the negative 6, and that's going to equal, does that work? So, and then that's going to equal, let's see, so that minus 0 is going to be 0, so we just multiply this by 1.0 times 10 to the negative 6, and we got this very small value, and that's going to be 1.57 times 10 to the negative 3 value, and it's a negative. As you see in the calculator, and this is going to be in terms of joules. So our answers are that right there. So we can write down over here where it says answer. We could write down 0 in chronological answer. Our answers were 0, negative 1.57. So 0 voltages, negative 1.57 times 10 to 3 voltages. And then the work was negative 1.57 times 10 to the negative 3 joules. And so if we check our prediction, and in part I, it says check your prediction, check your answers with your prediction. If we check our answers to our prediction, we predicted it will be 0 voltage because of the electric dipole. And in between, you're going to see that it's always going to be 0 if they have the same magnitude and equal distance apart. So therefore, we predicted before that was 0, and so that was correct, and that matches. The next one was VR. We predicted VR to be in the range of times 10 to the 3, negative between a value of 1 to 9, and we got that prediction right. It was times 10 to the 3, and then for our work we said it should be times 10 to the negative 3, which we got right here, and it was supposed to be negative. We got a negative sign, so therefore we could say my prediction and my answer seem to align in magnitude and also in sign. Therefore, following my steps and the problem guideline, my answer seems reasonable, and therefore I can conclude it's correct. And that's how you use the problem guideline to help you bring into the mindset of what are your main concepts, and then from then you could find your given information, like write down all your given information that you're given. Then you can say, okay, now I know what's given. We're just asking me like what are the final quantities I have to solve for in the units, and you know this is voltage, this is voltage, this was our joules. So that was a J. So and then we could also look at the diagram to help us predict the range and like understand like what we could predict. So if we're trying to predict, we could look at diagrams. If a diagram is given, we can think about it first, looking at the diagram and think about it a little bit, and you could predict the range real quick. And then you can also on part F, think about the equations you might need to use, and that's going to be our voltage equation and our work equation. And then from then you can answer your questions of A and B, or whatever scenario you have, whatever type of questions in this section, but in variable form. And after you've solved it in variable form, try to depict it to see, okay, what can I do to simplify it so when I compute it into the calculator, it could be done quicker, efficiency, and least likely to make a mistake. And try to always like add little notes to yourself. Was Q1 negative? Was Q2 positive? You know, just like those little reminders that could be very helpful. And another thing is after you get this, you just plug and chug and put it in your calculator and put all your units involved, and that's how you will get your answer after you plug and chug. And you write your variable form with numbers, so you just put your numbers, the form you used, and you plug and chug, and then you check your answer against your prediction before what you predicted and what you got. If usually they align, then usually it's right, unless you made an answer like, say you didn't compute 8.4 minus 4.2 to be 4.2, and you said like maybe 4. That's another way. So you just recheck your answer and just see if it's correct, and if it aligns with your prediction, you should be good to go. Solving your guideline is solving and knowing your knowledge, using your knowledge. And yeah, thank you for watching my video. I hope you enjoyed, and I hope you learn how to use the problem solving guideline. Thank you.